Section 5.1 is on polynomial functions. Here are a few vocabulary terms you should remember from Algebra 1. A monomial is a real number, a variable, or the product of numbers and variables. A monomial does not have any plus or minus in it. The degree of a monomial is the sum of the exponents of the variables. A polynomial is a monomial or the sum of monomials. The degree of a polynomial is the greatest degree among all of its monomial terms. A binomial is the sum of two monomials, and a trinomial is the sum of three monomials. So a polynomial function is defined by a polynomial with the variable x. Let's take a look at this chart from your textbook. Looks a little complicated. So the standard form of a polynomial function arranges the terms by degree in descending numerical order. So the term that has the highest power of x goes first and then on down in order. Now, here's the way we write it. P of x is equal to a sub n. So that's just the coefficient of x, and then n is the exponent. And then you would go kind of like to the second to the next one down, a sub n minus 1, and then x to the n minus 1. So for example, if n were 3, this would be x to the third, this would be x to the 2, and you continue going on down until you get a coefficient and x to the first power, and then a sub 0, which is your constant term. So n is a non-negative integer, and then the a sub n minus 1, a sub n minus 2, all the way down to a sub 0 are real numbers. So if you have a term that's raised to the third power, we call that the cubic term. Then something raised to the second power would be your quadratic term. Something raised to the power of 1 or without an exponent is your linear term. And then your constant term is the term that does not have a variable. Polynomials can be classified by degree and number of terms. So if the degree is 0, it's a constant term. So for example, 5. So that's kind of like saying 5 times x to the 0 power, because remember, x to the 0 is just 1. In this case, we have one term, and we would call it a monomial. If the degree is 1, it's linear, so something like x plus 4, that's like x to the 1. Degree 2, you would have an x squared in it, would be your highest power. A cubic would have an x to the third as your highest power. A quartic, x to the fourth, and a quintic, x to the fifth. Notice if there's two terms, we call it a binomial. If there's three terms, we call it a trinomial. And if there's four or more terms, we would just say a polynomial of 4 terms or a polynomial of 6 terms. Okay, let's take a look at an example. Let's write this polynomial, negative 3x plus 4x to the third plus 7x plus 3 in standard form, and we need to classify it by degree and number of terms. Well, the first thing I'm noticing is that I have two like terms here, so I need to combine those. So that's going to give me a 4x. But I need to rewrite it with my highest power of x first, so that would be 4x to the third plus 4x minus 3. That would be standard form. Its degree is 3, because that's the highest power of x, and the number of terms is 3, so that means that it is a trinomial. Also, the way we would refer to this using both of these, we would say that this is a cubic, because it's to the third power, trinomial. Now, the degree of a polynomial function determines its shape and its maximum number of turning points, or the places where the graph of the function changes directions. The degree and the sign of the leading coefficient, that is the coefficient in front of the highest power of x, determine what's called the end behavior of the graph. The end behavior is the direction of the graph at the far right or the far left. In other words, what is going on at the arrows on the end of the graph. A function is increasing when the y values increase as the x values increase, and a function is decreasing when the y values decrease as the x values increase. In other words, where is it going, up or down? So here's a table, a chart from your textbook, which goes over some of the different examples here. So here we have a quartic with a positive leading coefficient, and it looks something like this. The end behavior we describe as being up and up, because right here we have an arrow going up, and right here we have an arrow going up. The turning points would be kind of at these points right here, which they approximated probably using a calculator, and that's where the graph goes from going down, and at this turning point it starts going up, at this turning point it starts going down, and at this turning point it starts going up again. We say that the function is decreasing. That would be like on this interval here, and on this little interval here. That's where it's going down. And then it would be increasing on this interval here and this interval here. That's a very complicated graph. Here's one that's a little more familiar to you. It's a quadratic function, and the leading coefficient is negative. And notice its end behavior is down and down. It has one turning point right here, and the function is increasing on this interval right here when x is less than 1, and it is decreasing on this interval here when x is greater than 1. Here's a cubic function, the basic cubic function, y equals x cubed. Its end behavior is down and up. It has no turning points because it never changes. It's constantly going up everywhere, so it's increasing everywhere along this function. And our last one is a cubic function that has a negative leading coefficient. Its end behavior is up and down, and it has turning points here and here, and it is decreasing on this interval when x is less than whatever that value there is, and it's also decreasing on this interval here, and then it's increasing on this interval here. So let's take a look at an example. Oh no, here, before we do an example, here's a little summary chart. The end behavior of a polynomial function with the leading term a x to the n power. So a is your leading coefficient, n is your exponent. So if a is positive and n is even, your end behavior is going to be up and up. If a is positive and n is odd, it's going to be down on the left and up on the right. A is negative, n is even, down and down, and a is negative, n is odd, up on the left and down on the right. So the graph of a polynomial function with degree n has at most n minus 1 turning points. So we saw that. So we had a cubic function, and it can have at most 2 turning points. The graph of a polynomial function of odd degree has an even number of turning points, and the graph of a polynomial function of an even degree has an odd number of turning points. So let's take a look at an example here. So this says determine the end behavior of the graph of y equals 3x to the fourth minus 2x cubed plus x minus 1. So in this case, my leading coefficient a is greater than 0, and my n, or my degree, is 4. So referring back to our chart, a is positive and n is even, so my end behavior is going to be up and up. So in other words, the graph of this is probably going to look something maybe like this, okay, where it's going up on the left side and up on the right side. Here we get a little more complicated. Describe the shape of the graph of the cubic function y equals negative x cubed plus 12x, including end behavior, turning points, and increasing and decreasing intervals. The easiest way to do this is let's graph it on our calculator. So I've already put it into my graphing calculator here, and when I hit graph, I can see that I can't see the whole graph, and this is with my standard negative 10 to positive 10 viewing window, and I need to be able to see what is the minimum value down here and what is the maximum value up here in order to get the coordinates of those turning points. So I'm going to change my window, hit the window button, and what I need to change is my y minimum. So I think I will make that one more. I think I'm going to make that a negative 20. And then I need my y maximum. I think I'll make that a positive 20. And then I think I'll change my y scale to 2 so I don't have so many little marks. Now when I hit graph, I can actually see that I have a turning point here. It's not going to let me write on that, and I have a turning point right here. So what do I know about this? My end behavior is going to be up and down. I'm going to go ahead and write that. So my end behavior is up on the left and down on the right. I need to find my turning point, so I need to find the coordinate right there. So that's a minimum value. So I'll do second trace, I'll go down to minimum, and this is going to ask me for my left bound and right bound, so I'm going to move my cursor over to here to get to the left side of that. There's a little bit of delay in this calculator. Okay, anywhere to the left, I'll hit enter, and now I need to get over to the right of that minimum value. And I'll hit enter, and it's asking me to guess, and I'll hit enter again. And I notice that I have a minimum at negative 1.999. Okay, that's negative 2, negative 16. So I have a turning point at negative 2, negative 16. And actually, I'm not going to take the time to do it now, but if I were to do the same thing with this point up here, I would discover that that's the point, positive 2, positive 16. It always isn't always going to be symmetric like that, but that's the idea. Now, where is the graph increasing? And where is the graph decreasing? And I can do that just by looking at the graph, and now that I know the coordinates of my turning points, it is increasing from here up to here. So that was from negative 2 to positive 2. And I would write that as negative 2 is less than x is less than positive 2. Notice I'm not doing an or equal to. And then it would be decreasing on this interval here where x is less than negative 2, and decreasing on this interval here where x is greater than 2. Decreasing where x is less than negative 2 and where x is greater than a positive 2. Okay? And our last example gives us a table of values of a polynomial function, and we can determine its degree by examining the consecutive differences between the y values. If the first differences are constant, so when I subtract my y's and I get the same number every time, the function is linear. When I subtract the first time and then I subtract the second time, if those values are constant, then the function is quadratic. And if the third differences are constant, the function is cubic, and so on. So let's see what that looks like with this table of the polynomial function. So what I need to do is, and actually it doesn't matter which direction I subtract as long as I do the same way. So if I do negative 13 minus a negative 4, I get negative 9. If I do negative 4 minus negative 1, I get a negative 3. If I do negative 1 minus 2, I get a negative 3. 2 minus 11 is a negative 9. 11 minus 32 is negative 21. And 32 minus 71 is a negative 39. Okay, so that would be if n were equal to 1. If it were a linear function, they're not constant, so it's not linear. So let's do our next differences. Negative 9 minus a negative 3 gives me a negative 6. Negative 3 minus a negative 3 gives me a 0. Negative 3 minus a negative 9 gives me a positive 6. Negative 9 minus a negative 21 gives me 12. And negative 21 minus a negative 39 gives me 18. So that would be, if it were a quadratic function, if those were all the same, it would be quadratic. But it's not, so let's keep going. So negative 6 minus 0 is negative 6. 0 minus 6 is negative 6. It's looking good. 6 minus 12 is a negative 6. And 12 minus 18 is a negative 6. Okay, so those are all the same. So that means that n equals 3. So this would be, so my degree would be 3. So that this would be a cubic function. So in this section we took a look at a lot of different aspects of polynomial functions. End behavior, turning points, what a leading coefficient tells you, what their graphs look like, and how to determine from a table what the degree of a polynomial function is.